Uh, Thanks a lot for this opportunity to speak to you today on the fire safety of high-rise buildings and facades. The issue of facades and fire safety is an old one. We are having continuous problems with our building designs under fire, and especially the facade systems are presenting a huge risk under developed fire circumstances. I'll just speak a few words about my organization. We are Effectus, the largest independent private third party globally on fire safety. We were originally the union of two national public bodies of Europe, Dutch National Research Center, TNO, and French Scientific and Technical Center dedicated to steel construction, CTICM. United combined their forces, merged their activities in fire safety in 2005, and set up Effectus Holding. And these activities are going as far as 120 years in respective countries. So they have been testing fire resistance for 60 years and having quite numerous experience on high-rise buildings and facades under fire conditions. Hocam sanırım lobide bekleyen var. Onları size bırakıyorum. So going on, we are a private body, however, publicly owned, and our locations are basically all around globe in our fire safety engineering centers, but our major locations are our laboratories, which are located in UK, Netherlands, France, and Turkey. Our second largest laboratory globally is in Turkey, in Gebze, organized industry zone, and out of this 6 fire testing laboratories, each and every one of them are, of course, ISO 17025 laboratory accreditation owners, and each and every one of them are accepted globally by ASTM, NFPA, or European Union, and locally by local bodies such as Turkish Accreditation Agency or the Qatari, the UAE Civil Defenses, etc. On the top right-hand side, you'll see our Effectus laboratory in Turkey. The last one, actually, we have built 3, and this is the final laboratory in 2017. We're building another one in Turkey right now, which will be operational next year, and we'll be building a new one in Qatar in 2022. Okay, this is globally us, and I think it's enough to speak for Effectus and what it does. Maybe a word. An international third party tests, inspects, and certifies construction materials such as facade members or such as insulation panels, as simple as insulation panels. We test, inspect, and certify materials, and we inspect and certify design or construction of buildings. So we are authorized to check a design, be it a architectural design or a mechanical design. It really doesn't matter. But of course, simply in the aspect of fire safety. So when it comes to fire safety, we can check, inspect, and certify from the material to the building almost anything. myself, actually, I'm an aeronautical engineer, not really an architect or a civil engineer as is expected. But since our expertise is in fire, mechanical oriented engineering's come in more handy, and I myself am an aeronautical engineer, I must say. However, our team has numerous different experts of different majors in the universities, including architects. So if any of you guys are interested or will be interested in the future in fire safety, we'll be waiting for your application, really. So I set up with my partner at the time, Turkish partner at the time, the first Turkish, fully Turkish accredited fire testing laboratory of Turkey in 2008 under my company, Era Laboratories Group, Era Company Group, set up in 2003 by me and my partner. Then we married, so to say. We inaugurated our union with Effectus Holding in 2011, and we became Effectus Era Avrasya. Era coming from our first laboratory, Era Company Group. I've been holding the position of executive committee member of Effectus Holding in France, in charge of this region, and the technical committee chair of IMSAD, the technical committee chair of IMSAD for structural fire safety, and the TK3 Fire Technical Committee Chair of TUKSA, Turkish Construction Steel Association, as well as many other national and international technical committee memberships and board memberships. Today I'll tell you a bit about initially how high-rise buildings are practically unique and different in approach when it comes to fire safety. Let's define what a high-rise building is, if you may. There are very different definitions around the globe for a high-rise building. But an example, the Turkish us, we are calling any building over 21.5 meters in our regulation, the Turkish fire code, so to say, the Turkish fire regulation. We are calling any building over 21.5 meters a moderate high-rise building. However, even if it's not uniquely defined, we have in our regulation, in tables, and in applications, a different level of high-rise that we may call a very high-rise building. That the demands from the building is different. The active system demands and the material selection demands, so passive system demands, are very different. And that height is 51.5 meters. So there is a high-rise building that you may call 7 to 8 stories and above, and a very high-rise building that you may call, so to say, 17 to 20 stories and above, 21.5 meters and 51.5 meters building heights that are defined in our regulation. But if you go to France, for example, you'll see a high-rise building level of 28 meters for every building except housings, except occupational buildings, and 50 meters for housings. However, the skyscrapers, the very high-rise buildings, are the ones that are exceeding 200 meters. So the regulation defines what a high-rise building is. So the market you are working will always define you the limitations you'll have in your building designs based on the height of the building. So the general fire safety concepts that are used when you're designing a building is how fast you can get the occupants escape, or how quick can the fire brigade extinguish a fire or suppress a fire, and how can we avoid the fire spread to the surrounding buildings. However, these general approaches are practically deadly, mortal in high-rise buildings, because if you try to get the occupants escape a high-rise building, you'll be dealing with hundreds of people trying to escape, trying to egress the building at the same time as fast as possible, where the fire brigades try to find a way to enter the building amongst all these civilians trying to escape. And practically it will be impossible to avoid the spread of the fire to the surroundings, because there will be people around. No physical precaution will be available at the time. So the general approaches causes panic, accidents, and cultural damages. So we will need a different set of rules when it comes to high-rise buildings because of the height. So the escape route distance, a very heavy, very long escape route distance, and the high number of occupants inside the building. So the strategy for high-rise buildings are very different, actually. You have to maintain the people as much as possible where they are, and only egress the people from the directly affected area, not to outside, no, but to the closest safe location. And this defines and changes the design of buildings, really. The work that will be done by the architects and the civil engineers are completely different in a high-rise building. Okay. What happens if you fail? What happens inside the fire, inside the developed fire, especially after 1 hour? To heavy concrete load-bearing slab here. This is the inside of one of our furnaces that we tested several years ago. This is a C45 concrete load-bearing slab, which was really required to withstand 3 hours of fire, because it was designed to become the load-bearing basis, the load-bearing basic wall under a high-rise office building, a business building. Let's see what happens if you don't do it correctly. By the way, inside the furnace right now, after 1 hour, is roughly 950 degrees, reaching to 1000 degrees. There is a special camera that can record under this heat, that can resist up to 1350 degrees, that is recording it inside the furnace right now. So you're saying that inside a fire resistance test, the flames do not touch the element. The specimen that you are testing is not flame torched or something like that, but the environment is continuously heated. The sound of the fire, the sound of the gases you are hearing is coming from the burners, the furnaces burners. Under very heavy energy levels, we are increasing the inside atmosphere of the huge furnace that is 4 meters to 4 meters to 3 meters, so 48 meter cube, and we test a 4x3 wall element like this. Have seen the explosion. There was an explosion, something like that. Really explain the material itself that is exploding. Now take care of left upper side. Yeah, has exploded as well. Now Now you see this second product, which will be exploding sooner. Then you see an imminent collapse of the lobby. Collapse is coming, you see it's going, and you have lost your building in 1 hour. Why? What happens? We are taught, we are continuously reminded that the concrete doesn't burn. Yes, it doesn't. Because for burning, you need organic materials, and the concrete does not contain any organic materials. But fire resistance is not burning. Fire resistance does not require your products to burn. There is always something to burn in buildings. The buildings are more and more made from elements, plastics, petroleum chemicals, petroleum-based chemicals, less natural plastics, we might say, like aluminum,
Mr. İlker, we cannot hear you clearly. Is there a problem with your microphone?
Oh yeah, probably.
We cannot hear you clearly. Sesiniz gelmiyor İlker Bey. Hiç gelmiyor. İsterseniz çıkıp tekrar girseniz belki faydası olur mu? Şu an hiç gelmiyor sesiniz.
Evet, dondu. Yani görüntü de dondu.
Evet. Geldim geri. Nasılız?
Sanırım şimdi daha iyi.
Tamam.
O videoyu açtığınızda sesiniz bozuldu. Video bitti ama sesiniz düzelmedi.
Tamam, oldu. Yani en azından videoyu seyretmeye çalıştığınız videoyu baştan seyrettirmem gerekmeyecek.
Evet,
Süper.
videoyu izlettirmeyin tekrar. Şu an sesiniz yarık.
Oradan devam edeyim.
Evet,
Demek ki videolarda problemi yaşayabiliriz.
Evet.
Back to
Ekranı
the
paylaşır
topic.
mısınız?
Pardon, haklısınız. Pardon. Okay. Tamamız değil mi?
Not yet. We cannot see. I cannot see your screen.
Hayda. Bakalım niye? Bir daha deneyelim.
Yine göremiyoruz.
Bilmiyorum, bir fikrim yok. Ana ekranı paylaşmaya çalıştım ama göremediniz. Şimdi bir de dokümanı paylaşmaya çalışayım
Evet,
bakayım.
direkt PowerPoint sunumu paylaşalım belki.
Evet. Belki o işe yarar. Hayda. Stop sharing de yapmama izin vermiyor şunu. Peki.
İsterseniz
Ben bir daha
tekrar mı çıkalım?
girip çıkayım. Evet,
Evet.
tekrar girip çıkayım.
Tamam. Çıkamadınız henüz.
Hı hı. Evet.
Ben sizi çıkarayım mı?
Lütfen, size zahmet.
Tamam.
Evet. Ben geri geldim. Sesim
Sesiniz harika.
tamam, görüntüm de yerinde. O zaman önce bir screen share yapmaya çalışalım. Ekranı
Oldu.
geldi. Tamam.
Oldu.
Oldu. Hemen sunumu açarak başlayayım. Tıt tıt tıt. Sanırım bir problemimiz yok değil mi? Sunum
Yok.
görülüyor.
Yok, sorun yok.
Tamam, kendine geldi makine demek ki. Video ağır bir video. Demek
Evet.
ki kilitledik makineyi. Tamam. Kaldığım yerden devam ediyorum. Basitçe videonun yorumuyla ve İngilizceye geçiyorum. What we have seen in this video was a concrete slab of C45 with 60 centimeters thickness that should have resisted the fire under standard fire testing conditions up to 3 meters, up to 3 hours, sorry, because it was meant to be the main load-bearing wall of a high-rise business tower. But it collapsed after 1 hour. Although the concrete does not burn, it doesn't mean it is fire resistant. Burning and fire resistance are, two different things. And something that does not burn, it really doesn't mean that it resists fire, because inside our buildings, think about it this way, inside our buildings, we have many materials, and all these materials are susceptible to burning. They are ignited and they burn along the way when the fire starts and develops. Because our materials are basically polymeric. They are polycarbonate-based petroleum derivatives, like plastics, any kinds of plastics, or even if they are, let's say, metallic composites, like aluminum composite panels, the most of it, 85 to 90% of it by mass, is polymeric. Like polyethylene, high density polyethylene in aluminum composite panels. So what happens? These materials burn and they increase the temperature inside the building. And when temperature increases up to a certain level, in this fire resistance test, we were witnessing a temperature level inside the burning hole up to 1000 degrees, 950 to 1000 degrees. When the temperature increases to that level, because concrete is a mixture, really. It is a mixture of water, up to 8%, of cement, and different minerals. And because cement is not bound, is not really becoming concrete without hydraulic bounds, it requires water. So water all around the world boils at 100 degrees. We all know it. And when the outside temperature is 1000 degrees, so the first hour of a fire, the temperature inside the concrete reaches up to 300 degrees. And 300 degrees inside the concrete means you'll have a water vapor pressure of air and water gas. And this water vapor pressure increases the pore pressure, meaning that all the small pores, all the small cavities inside the concrete will be under tremendous water vapor pressure. That is the exact equivalent of what made in the old times the locomotives run. We used to have water vapor locomotives. Locomotives for trains that are running on water vapor in the first years of the train history. So at 300 degrees of inside temperature, the concrete is now under compression stress from the heated surface, and the thermal difference, the thermal gradient, so to say, creates a cracking mechanism inside the concrete, because the outside is hotter than inside, up to 600 to 700 degrees, and this kind of temperature difference makes the materials go under a compression stress. Moreover, there are different materials inside concrete, such as the aggregate, the cement, the metals like steel meshes or steel rebars. And they all try to move in different ways. They all try to really act by themselves, thus creating a cracking mechanism inside the material as well. And finally, there are chemical transitions starting at 1000 degrees. Nothing is really very resistant under an hour of fire development reaching 1000 degrees. So the strength loss due to these chemical transitions finally allows the material to spoil, to crack, and from time to time to explode, as you have seen in the previous video. So now we know that if you do not really design the materials, and if you do not really design the building elements correctly using these correct materials, the building is not really resistant up to a few hours, which is required to limit the damage given to people and the building or the surrounding buildings. We must think about a new way to let people understand what to do under fire conditions. First of all, the building should be establishing trust among its occupants, and the occupants should be able to communicate inside the fire to allow the panic not to rise, really, and to allow people to escape under directly affected areas to the safe places, to the safe havens, so to say. And the people who are living in the places that are not affected by the fire imminently should be kept as long as possible until the people under risk are evacuated at least. And we should avoid the structural collapse. Meanwhile, keeping the building intact. And for that, we need to manage the heat and the smoke. The heat is critical for the structural collapse. However, the smoke is deadly for the people living inside the building. So, yes, all these limitations requires a strategy to manage the fire safety of a high-rise building. And this strategy really is not delivered in codes or regulations, because the codes and regulations are always prescriptive, meaning they tell you what to do under standard conditions. And when the conditions change and they're no longer standard, you need optimized solutions, not standard solutions. So the prescriptive regulation become not really safety driving in this case. So the approach to fit the high-rise buildings and many other specific attention required buildings is called the fire safety engineering. The fire safety engineering, so to say, defines the performance space. What is the performance space? The performance space is how your building should act up to how much time under which kind of fire. So first we should define the possible fire scenarios, making a risk assessment, seeing what the building really generates as a risk. We have to approve this risk assessment by the local authorities, of course. Then we will work up to increase the global fire safety of the building using engineering. We select our materials by this engineering, and I'll explain how it works. And then we are even able to save some costs, up to 3% in design and building expenses, based on a 20-year study made by European Union that started in the 1990s. And we have to manage the complexity of this fire safety engineering using fire safety experts. So, what does fire safety engineering provide? You identify your worst case scenarios, meaning there are more than a single way for a fire to start. And some of these ways are really messy. I mean, really, the cases that you do not want to see in your continuous life. But one or two of those cases are the crucial ones, the critical ones. And you have to design your building based on the worst case scenarios. Because if these cases arise, logically, under acceptable and logical conditions, if they arise, then your precautions may fail. So you have to take your precautions based on the worst case scenario. Then the fire and smoke development model is developed by the fire safety engineer. The fire and smoke development model defines, given this worst case scenario, how the fire will be generated and how the smoke will travel inside the building. Then the smoke and the fire will be carrying heat, of course, and this heat will be affecting load-bearing elements such as walls, columns, or we can say all lateral and horizontal load-bearing elements. And these elements are the basis where our building is holding its structural integrity, of course. Thus, we have to check how they act, how these elements act using heat transfer models. After the heat transfer model is done, we can move on and check a structural behavior model And finally, when we make sure that our building resists fire under given conditions, let's say 2 hours in the worst case scenario, when we are sure that it will not collapse, then we can think about how to evacuate the people, thus the egress modeling. So the modeling results are really, when I come to the previous slide, are really colorful figures like this you see down here. And if you're not an educated eye, it really doesn't mean anything. However, it's based on hours and weeks, actually, not even hours, weeks of data work under CFD applications, computational fluid dynamic softwares, such as ANSYS, for example. And you need an engineer to develop the architect's idea and the civil engineer's application into a fire safety engineering model to check what is really happening inside the fire based on your given design, which concludes in the approval or validation of the fire safety of the design. So I just wanted to give you a small hint of how fire safety engineering works, because we will refer to it in the next chapters of our presentation. But after the design is done, after your work is done, the second work, which is even more crucial for the safety of the building, which is the construction phase, really. Because even if you design everything correctly, even if you select your materials correctly, even the best materials and even the best designs fail to perform if it is not properly manufactured and assembled in location. So correctly installed, of course. And most of the cases at the construction site, there is economical and time pressure, always time pressure and always economical pressure. So the training is most of the times amiss, it is lacking, and the understanding of installation essentials doesn't really include fire safety. So that is amiss as well. That allows to fire-wise underperforming products and installations. The solution there globally is inspection. So some educated third eye, the controlling body, the third-party inspection body, is checking that the structural elements and the fire critical elements are installed as built, and the design is really constructed as meant. Thus, everything is okay. And finally, the lifetime phase shouldn't be forgotten, because the building is aging. And when the building is aging, the initial assumptions of the building usage, the usage of the areas, etc., really doesn't work like that, because with the age of the building, in most of the cases, the areas are shifted to different usages, increasing its risk, the fire safety risk, and the installed equipments are not really there or working anymore. So throughout the lifetime phase, the buildings should be continuously controlled and checked. Especially in industrial buildings, this is a legal requirement in our country. However, unlike some more developed codes, let's say, in some countries like USA, UK, or Germany, or France, we don't have continuous surveillance controls in our non-industrial buildings yet. We are hoping it will arrive sooner with the code revisions. But right now, at least the industrial buildings are mandatorily checked for fire safety regularly based on the Turkish code. Okay? So let's change the topic. What can be checked? This list covers, based on the regulation, what is checked really? The construction materials and elements, the fire compartmentation, like the technical areas, car parks, bunkers, heating pump stations, etc. The roof, of course, the fire stairs, the fire and smoke zones and safety precautions in those zones, fire escape routes. You see another fire development model on the side, by the way. I just scattered some figures over there. So most of the cases, everything that is susceptible to burning and susceptible to develop fire, and everything that is meant to stay there inside the fire process, such as emergency lightings or the installations to active systems, water mains, etc., or sprinkler systems, etc., they are checked in a third-party inspection, either structurally, architecturally, or mechanically. Okay, let's pass this area, this first part of the presentation, and switch to the next part of our presentation, keeping check in time. So the first conclusion, the conclusion of the first part of my presentation is that a high-rise building can be, and in most of the cases, a correct solution to enable a very high density of population, such as Istanbul, Ankara, and Izmir, and to keep them in workplaces, in accommodations, in public buildings, etc. You will need to design high-rise buildings. And the third dimension is in most of the cases the only way you can go, because there is not enough land or it's too expensive. But the level of risk associated with such a high concentration of people, where the firefighting is a problem really, the egress of the people and the smoke control is a problem really. I mean, you need a different aspect. You will need a third eye. You're not building really any longer a 5-story family house. You're building a high-rise building, so the risk will increase and multiply. So if we do not forget that in the design phase, in the construction phase, and at least as important as the former two, the lifetime phase, the building should be dealt with fire-wise by the experts, that is the fire safety experts, fire safety engineers, and the construction and building of a high-rise building is a teamwork really. It should be done together by the architect, by the civil engineer, by the mechanical engineer, and by the fire engineer. Then you may assume safety based on the fire occurrences, probable fire occurrences that your building will undergo. So let's pass to the second part, which is the facades. And as I mentioned earlier in the start of my presentation, the facades still propose the highest risk we have been seeing in the last decades on the public health and people's lives actually, as well as the safety of the buildings itself, the structural safety of the buildings itself. Most of our 87% of our deadly fires where there are mortal losses, we see facade fires. So we should start by referring to our regulation and see what our regulation says about facades and facades in high-rise. So the final regulation we are using is the 2020 version. However, the July 2015 version of the regulation defines the final elements about high-rise buildings and facades. the last version, the 2020 version, is not revising anything about high-rise buildings and facades. So we can take the 2015 version of the regulation as our basis here. And when we look at that, we see the regulation demands two basic things: the fire resistance classification for all structural elements between 30 minutes to 180 minutes based on R, E, and I criteria, which is load bearing, insulation, and integrity criteria. And the regulation demands all construction elements to be used in the building to be classified to reaction to fire classes between A1 and E. For the fire resistance classification for the structural elements, we have two fully equipped laboratories in Turkey. The first one historically is the Effectus laboratory, our laboratory in set up in 2011. We have 3 of them right now. And there is also the TSC laboratory that was built in 2017. We have one TSC laboratory as well. So there is the public and private laboratories available in the country to test for fire resistance classification. Therefore, the construction industry is not really facing any difficulty to undergo this regulation requirement anymore. So the reaction to fire classification, we have more than TSC and Effectus. We have also manufacturer union laboratories and even insurance company laboratories like Allianz, for example, that are testing reaction to fire classes of construction materials under TÜRKAK accreditation. And this classification is mandatory for each and every building to be used inside the building based on the clause 29 construction materials clause of the regulation, and I'll come to that. So the initial point I'd like to highlight, referring to the building code, is the responsibility. Because you see, before the 2011 the initial issue of the Turkish fire regulation, the responsibility was basically of the fire brigade, as we call it, İtfaiye. So the fire brigade right now is one of the most unresponsible parties included in the system, because they don't have any authority anymore. The authority to issue building permits is not theirs anymore. The building permits are issued by the municipality and the ministry. The fire brigades are just supporting the municipalities by their inspections and issuing reports for the municipalities, of course, but the building permits are issued by the municipality itself or the Ministry of Construction, we may say. So the first responsibility is the public office's responsibility to issue correct permits for building and usage, of course. But this does not omit the second, third, fourth, and fifth line out of responsibility, really. The investors, building owners, employees, and representatives of employees are the owners of the building, the runners of the building. Thus, they are fully under responsibility of the building's compliance to the fire regulation. Then comes your and our responsibility. Your as architects, our as engineers. We are responsible for design and application of the building. We are legally responsible in case of a fire. A public court can be demanded based on this regulation, because we are required to design and apply the installation based on the regulations requirements. Then comes the consultants, the project managers, the controllers. That is again you and me, the engineers and architects, and the responsible parties inside the the construction site, so to say, the controllers, the managers, and the consultants. And finally, the operation responsibles and building control are all responsible side by side. Thus, we are punishable by law. We shouldn't forget that. So, let's try to understand what our requirements are for materials for fire safety, very basically, very roughly. First of all, we must know what reaction to fire is. BYKHY, binaların yangından kontrolü hakkında yönetmelik. So, the Turkish of the fire regulation, at Annex 2C or 2Ç, the reaction to fire classes of materials are delivered. And you'll see there is 4 different description of these materials. Hiç yanmaz, non-combustible, zor yanıcı, hardly combustible, zor alevlenici, hardly flammable, normal alevlenici, normally flammable. So these descriptions are actually referring to standard classifications. And this standard is Turkish standard European norm 30,501-1. This code defines A1, A2, B, C, D, and E classes. There is no B1, B2, B3. That is a very old, obsolete knowledge from 20 years ago. There is A1, A2, B, C, D, and E only. Okay, and I'll tell you what they stand for. First of all, the standard itself requires all construction materials to be tested based on its application area. If it's a construction product and element horizontally and vertically, except the floor coverings, or is it a floor covering, or is it a linear pipe insulation? So based on these 3 criteria, to be tested to the below 5 standards, 1 to 5 you will see. And these 5 standards are really 5 tests. First test is the room corner test, so-called SBI, single burning item test. The room corner test emancipates to control the evaluation of fire in a room corner inside a house, started by the burning of some non-plastic material. In this case, textile and wooden-based material, fiber materials are taken into consideration to calculate the fire load. You apply the material you will test inside the testing chamber as a corner of 1 meter and half meters in length. So it's an L shape, half meters the short part, and 1 meter the long part, and 1.5 meters in total. So half meter to 1.5 meter, 1 meter to 1.5 meter, you reach 2.25 meters square of area of materials designed as a room corner to be tested for the fire start. So this test checks how the fire starts, how the flame develops, how much energy will be released from the material, so the heat value of the material itself, how much smoke is released, and what is the smoke average dissipation, which is oxygen to carbon monoxide and carbon monoxide to carbon dioxide values. And because carbon monoxide is the basic of suffocation, of course, inside fires. And then you'll check how fast the fire will develop, checking the acceleration of the fire growth rate, figura. So in this test, you will see a burning material, a material that can burn under fire starting conditions until the fire is a developed fire. The reaction to fire testing, all these tests beforehand, I must say, are dealing with the starting of the fire. So the fire phenomena can be divided in two basic timelines. The start of the fire is between the first to 5 minutes. 1 to 5 minutes is the start of the fire. The first 5 minutes really defines how the developed fire will be affecting your building. So the first 5 minutes, the fire developing phase is very critical. And the reaction to fire tests are dealing with this first 5 minutes, really. They are checking if a material can be burned and how fast the fire develops from this material, how fast the smoke will be developed from this material, and what is the energy to be released from this material to check if the fire will be developed and the smoke will be a mortal risk to the occupants or not. Test is for the materials that cannot burn, because you have metallic materials and like concrete or natural stone, mineral-based materials that you cannot really burn, that cannot catch fire. So we test them for non-combustibility and heat of combustion to check how much they will lose their mass, how much heat they will release, and when exploded, this third test is explosion, the heat of combustion test. Thus, it's called a calorimetric bomb. It explodes the material and breaks all physical bonds under 30 bars pressure of oxygen inside this test cabinet. So we check how much the bond energy, the internal thermal energy of a non-burning material is. We check this non-burning materials with these two tests to see if this material is really A1 or A2 class, so to say safe class materials or not. And also there is some materials that are burning very fastly, like polymeric foams. You see the XPS in the installed cabin being burnt in this picture. The XPS is extruded polystyrene, and such as XPS or EPS or polyurethane or polyisocyanurides, there are some materials that are very fastly burning. And these materials reaching burn rates up to few kilometers per hour. You will see my example a few slides later. A few kilometers per hour, they can burn at rates like that. There they are mortal. They are hazardous and completely mortal for the occupant safety inside the building. So they must be tested rigorously and under harder conditions, so to say. And the single flame test is the easiest test that is applied on them. If a material is burning under single flame test, it's no use, I must say. Then it's an F class, and based on our regulation, an F class material, a material that cannot even reach the lowest class of normal combustibility, E class. If the material cannot even reach the E class, it cannot be used in buildings, the regulation says. And the floor coverings radiant heat source test is the equivalent of the previous test for floor coverings. So, okay, we have spoken about these classes of A1, A2, B, C, D, E, and F. But really, what are these? What do they mean? Very simply, I'll try to explain. First of all these classes, the fire performance classes, so to say, they work with smoke production classes and burning droplet classes. Let's start with the easiest one, the smoke production. From weak to strong, how much smoke a material develops when the fire starts. S1 means that it is generating a really weak smoke or no smoke at all. it is perfect, really. S3 is developing lots of smoke. Then we come to the second additional class, the burning droplets. When a material is under fire, if it is dropping some burning droplets, it will very easily spread the fire to surrounding materials and surrounding buildings. So we must check if any droplets or particles are coming out of the material when it's burning. And again, from none to heavy, there is D0, not generating any droplets or particles at all, or D2, which is really raining fire. Okay, so these are the classes that work with A1 to F class. Each one of them is applied to each class. So let's try and understand what these classes stand for. I'll go very, very roughly, very easily, as the basic material knowledge, not into technical details at all. The first thing you must understand is only A1 class, according to TSEN 13501-1, only this classification of A1 is non-combustible. Because I have seen in the market for the last 20 years that I have been in the market, in the construction market, 20 years, that there are reports of A1 classes from some material manufacturers that are 20, 30 years old, that were tested to some national German norm, some German standards, DIN standard, so to say, which has nothing to do with this non-combustibility classification at all. The same tests are not applied, and materials that are A1 class to the old DIN norm, the German norm, are when tested to TSEN 13501-1, they are mostly B2C classes. So they are burning. They're not non-combustible at all. So this classification does not based on the same testing methods. So the result is not the same, of course. The TSEN 13501 is coming from the Euro norm 13501, the copy of the Euro norm in Turkish. And even in Germany, for the last 10 years, this one is applied. They are not using their old national code as well. So the material manufacturers should quit using the old norm and presenting the old test reports from time to time in the buildings. This is the first thing we must understand. The classification should be based on EN 13501-1. If you all agree on that, we may see what these classes stand for. The A1 class, or so to say the non-combustible class, are the materials that do not contribute to contributing to fire, do not contribute to fire, do not contribute to burning or smoke development characteristics under the fire. They do not emit any energy. They do not create any smoke. They do not really contain, except very minimum. Even unimportant levels, they do not contain any organic materials inside them at all. So where the organic substance content is less than 1% by volume and weight, we consider the product, we assume the product to be A1 class, and we test these products based on these two standards I told you about, the non-combustibility testing and the calorimetric bomb testing, to see if they really are A1 class. Then comes the second class, A2 class. These are the limited combustible, zor yanıcı as defined by the regulation. The limited combustible, or hardly combustible, you can say, are basically materials that are referred as the minimum class for fire safety in our building regulation, and we will see about that. Step by step. So most of these products are inorganic products. cement-based organic where organic binders are not used, mineral wool-based or gypsum-based, etc., that do not have organic layers, etc. And these products, like mineral wool or gypsum or cement-based or aerated concrete concrete-based, as known in the market, Yutong-based materials, they are mostly used for fire safety already. Then there is the B and C class and D and E class. B, C, and D class are basically different levels of the same characteristic. They are hardly flammable or normal flammable, except the E class. There is a specific point in the E class. These B, C, and D class materials are mostly creating smoke at levels. They are mostly creating energy, thermal energy at different levels. Most of them have polymeric substances instead, heavy to low. The lowest polymeric substance and the lowest risk is at B class. Then highest polymeric substance and highest risk goes to D class. Polymeric materials like polyurethane, polyisocyanurate, PVC are all in this level. And E class is the lowest level of normal flammable. They are heavily flammable. Under even a small flame attack, they can burn, such as polymeric foams, asphalt, bitumen, or paper, like wallpaper products. All right. Now we have understood. Let's see how facades are. By the way, I'll stop in 10 to 15 minutes maximum. My limitation is 12:15. I'll stop there. No worries. So to the regulation, the facades are required to be hardly flammable, so minimum C class, C, S3, D2, when the building is not high. When the building height and the facade height, so to say, is less than 28.5 meters, then the building can be covered with a C class facade system, hardly flammable facade system. This is the general rule. If the building is higher than the 28.5 meters building height, that is from the base level to the below roof level, of course, then you will need a stronger, for 29 meter of building height, you will need a stronger fire safety. Then you will go to A2 class, limited combustible or hardly combustible class, A2 class of material for all facade materials, every one of them. Okay. Then you come to the second phase. I don't go into many details because I have some slides left and you can easily read them. Then you come to the second phase. If the facade is covered by a conventional facade system, which is ETICS. ETICS is extended thermal insulation composite system, or known in our market by the wording mantolama. If it is covered by such a system used by thermal insulation material, thermal insulation adhesive, anchor, render mesh, render, and similar other equipments as defined by the regulation itself, then after the system is tested and certified by an accredited laboratory according to the relevant standards, and seen that it is minimum C class, it can be put on the market. However, be very aware, most of these systems are lower than that. First of all, most of these facade systems, mantolama or ETICS systems, are really made from insulation materials that are polymeric foams like EPS, XPS, or polyurethane. And these materials do not enable them to be A class at all. They stay in between B class to D class. Some of them, which are B and C class materials, can be used under 28.5 meters. But some of them, which are D class, cannot be used even in low-rise buildings, two-story buildings or something like that. But they are in the market. We must be aware when we are choosing them. And the ones that can be used in high-rise buildings are only the ones that have A class. And to be A class, by the testing methodology, they must have no polymeric materials inside, none of them. So only ethic systems, conventional facade systems that do not contain any polymeric materials, any plastics, can be used in high-rise buildings, such as the ones that are A1 or A2 class mineral wool containing facade systems. Okay? We pass. Okay. We pass to the next point, which is the insulation of some elements inside these facade systems, where the building height is less than 28.5 meters. I told you that we can use minimum C-class materials, but even if we use that, even if we use this facade system, we should insulate with some harder material the first 1.5 meters of height of the building. Why? What happens in the first 1.5 meters of height? The cars are parked and the garbage cans, garbage bins are located. So the garbage bin fire or the car fire can very easily torch the facades in this first 1.5 meters. So this first 1.5 meters of the building are required to be additionally non-combustible A1 class material. Then you have some openings where the fire can easily spread from inside the building to the facade, which are, for example, windows. So these openings should be additionally insulated 15 centimeters on the top and bottom, and 30 centimeters on the sides. No, just the opposite. 15 centimeters on the side and 30 centimeters on the top and bottom, but with class A1 materials for fire barriers. Okay, and finally, there are the curtain walling systems, of course, which we call in Turkish giydirme cepheler. The curtain walling systems are the most used insulation systems for our facades. And for the regulation in the 2015 version brings a direct limitation of using of this curtain walling systems with A2 class criteria. It says, open joint and ventilated curtain walling systems used in the buildings must contain facade and insulation materials of minimum limited combustible, which is minimum class A2 S1 D0 classes. Are there any non-ventilated or non-open joint curtain walling systems? That is the question. Yes, the joints are closed. It's not open joint. Turkish do not use the open joint, but more or less all of our curtain walling systems are ventilated, because the ventilation, the natural ventilation, so to say, is the gap between the outer wall of the building, where the curtain walling is applied, to the curtain walling system. It's not really filled by the Turkish, so that the excessive heat and the moisture can escape to the atmosphere and does not really create a moisture effect or a heat combustion effect inside the curtain wall. So we tend to keep, I mean, in most of the cases, not even most, majority of the cases, more than 90%, we tend to keep our systems as ventilated systems. So when the system is ventilated, naturally ventilated, so there is a gap, an opening behind the curtain walling system, and between the curtain walling system and the outside wall where it's installed, then the system must be A2 class, minimum A2 class material. So if that is not the case, if somehow there is no gap left there, under 28.5 meters, you apply the general rule. You are able to use the C class, but over 28.5 meters, so to say, over 7 to 8 stories of buildings, you must again apply A2 class anyway. What is the problem here? Why am I really referring to these classes? Okay, why? Very simple. Let's check what happens to fire, what happens to facade material inside the fire. If Koray Bey, if my voice fades again, please let me know. So I restart. You'll see, yes, here you see the upper view of our furnace, large furnace. We have 3 of them. That is 4 meters by 3 meters and 4 meter high. The material that we test is covering, facade and roof covering, used for both purposes. And it is called sandwich panel, actually, used for facade covering and roof covering in most of the industrial sites and in many high-rise buildings. Okay, so they contain, this sandwich panel here contains 100 centimeters of thickness of polyurethane, and the top and the bottom layers are metallic. Okay, 100 sorry, not centimeters, 100 millimeters, 10 centimeters, 100 millimeters of 10 centimeters of polyurethane, and metallic covers up and bottom. And the fire is inside the furnace. It's not touching the material before you ask. This test should have lasted at least 60 minutes, but it is automatically terminated after 6 minutes, and you will see why. Yes. You see the smoke development. Sesimi duymaya devam ediyorsunuz değil mi?
Evet, evet.
Süper. You see the smoke development. In the first few seconds, the smoke starts to develop, and it is emitted through some little openings of the insulation on top of the furnace. Okay. This smoke, be aware, this smoke is polyisocyanurate smoke, PIR smoke. Polyisocyanurate or polyurethane are 2 very similar substances that generate cyanide acidic or ureic acidic in the smoke. And cyanide and ureic acidics are both of them very heavily poisonous and very heavily lethal to more or less every living being, be from plants to animals to human beings, of course. It is the acid of the poison cyanide, cyanur. So this smoke is only generated after 30 seconds, and be aware 10 centimeters of this material with 4 meters to 3 meters in dimensions is only 1.2 meter cube of materials, 1.2 meter cube. And our laboratory surface is, this is the first initial laboratory. It was 1,200 meters square with 11 meters of height. So roughly 12,000 meter cube of air, 12,000 meter cube of air is being filled with only 1.2 meter cube of material. So it is filling 10,000 times of its area just in a few seconds. Okay, and there is still no fire, so the test is continuing, but we have already left the laboratory because of the heavy poison. I'm taking it a bit further. And from now on, yes, just back. Yeah, from now on, even the camera does not see anything. Just on the 6th second, the fire starts outside of the material. Does it really mean that fire is starting after 6 minutes? No, it really doesn't mean anything, because the smoke before the fire is there, the smoke has already killed everyone. There is nothing living in this thick smoke or in this fog of cyanide acid. Everything is dead. So it really doesn't matter if the fire is spread or not, as long as poisonous smoke is there, it is lethal as well. So this is the critical point in facade materials. That's why we require minimum C class when the building is less than 28.5 meters, and A2 class when the material when the building is higher than 28.5 meters. This material is C class, by the way. Okay, just 2 examples, then I'm closing my presentation. One example is Polat Towers. Okay. 1707, not 2017. The year is wrong. It was 2007 actually, 2011 actually. Let me correct it. It's just a mistake I did. 2011, not 17, of course. It has been 10 years. So a hot summer day in Istanbul, in Şişli, one side of the Polat Tower is completely burned. Why? Why didn't it spread to the second and the third site just 10 years ago? Very simple, because the sites were insulated, the rest of the sites were insulated by mineral wool and concrete. But the material here that completely burned down was aluminum composite panel, ACM. Aluminum composite panel, you will see, burns like this. The total fire height is 140 meters, 140 meters, all right? And the flaming time, the burning time is 3.5 minutes only, 210 seconds. So the average burning rate is 66 centimeters per second, or 40 meters per minute, or 2.4 kilometers per hour. So if there is anyone, any young guys over there, which is, high built, if there is anyone that is near 2 meters of height, just count to 3, stand up and count to 3. And when you count to 3, in this fire, from your toe to your to the top of your head, you'll be burned. So 3 seconds, 2 meters. This is how fast the fire developed. And the fire brigade optimal reaction time in Istanbul is 5 minutes. So even before the fire brigade was there, the fire was over. So the question was, what would happen if there wasn't an insulation to the sites? Such a fast fire, how would it burn? And we saw the answer. Just 6 years later, again, very nearly the same days, not the 17th of July, but 14th of July, a hot day in London, we saw the Grenfell Tower fire. And the Grenfell Tower fire, there was no insulation between the parts of the facade, and it all burnt down, killing 72 people. It only took 12 minutes for the fire to start and completely spread in 12 minutes inside in the middle of the night, completely spread to the facade. Due to a large fridge freezer burning inside one of the kitchens, the PVC window melted down, and the same material, aluminum composite cladding panels, were ignited, and basically just in an hour, it was impossible to escape from the fire, because the smoke filled every one of the lobbies, killing 72 people. So why is that? Why materials are killing people. Very simple. This example is one of the easiest examples, the aluminum composite panel example. You have aluminum sheet on top and in bottom, and you have the insulation core, thermal insulation core, meant to be there for years, which is polymeric. In this case, high density polyethylene, HDPE, HDPE. All of these polymeric cores, non-metallic cores used in the facade coverings, they are inflated either by hot gases or by hot water vapor. And it really doesn't matter what it is filled with. When it is facing summer sun for a few years, it starts to lose its gas, or its water vapor goes out of its entity. And when it loses all its vapor and gas, it becomes fragile. It becomes like gevrek, really, burnt gevrek. It really becomes very easy to burn. So just at a condensed heat on top of the aluminium under the summer sun, it burns by itself. Or in the Grenfell fire situation, with a small flame in the PVC, it can burn by itself, killing many and many people. Okay. I put some report findings, and the link to the report itself for anyone that is interested. How Grenfell fire in the middle of London killed so many people just 4 years from now. You can read it, but it's saying we shouldn't use flammable materials. It is the national inquiry, the official inquiry run by a judge, a high judge of London. We shouldn't use flammable material in high-rise buildings. It says every material must be tested and certified. The judge says, and the evacuation methods, partially and full evacuation methods, should be developed specific to high-rise buildings, it says. So everything I have told you in the last 1.5 hours is already regarded after the fire in the UK report. All right. So one more example, then we close. Just an information, really, not really an example. Based on the Istanbul Grand Municipality fire statistics in 2012. Why 2012? Because from 2012 to the change of the municipality management 2 years ago, the statistics were ceased. It wasn't aired anymore. Now the new management of municipality are starting to gather the statistics again to issue. So it was an average year, and 25,000 fires started in Istanbul. 13,800 fires were building fires. So in 13,800 buildings, there were small partial damages. However, there is a figure that is very, very frightening. 706 buildings were completely destroyed in 1 year only, non-usable buildings. 700 buildings. Out of these, most of them are production plants. 569 of them are factories or industrial applications. And let me tell you this much. The average number of casualties we have in Turkey every year is 400 to 480. Okay. And again, this is the statistics from 2012. 400 to 480 people every year is dying in fires in Turkey. And every year we are losing the double of what Istanbul loses as buildings. 1,500 buildings are lost every year in Turkey. So the question is, why don't we read about such fires every day in the newspaper? The answer is very politic and very easy. Because it's not news anymore. It doesn't contain news material anymore. If there is not a public outrage about a fire killing many people at the same time, it is not news anymore. So this 400, 450 people are only underlines in the third or fourth pages of newspapers, not in the evening news in the televisions. And the problem is we have fire statistics that are 2 to 3 times more than Europe. Even 1.5 times more than Russia. So I can say easily that at least half of these people that are dying every year can be saved if we can design and build our buildings correctly. So, discussing this, I'm coming to the result. As a result, in buildings, the regulation must be conformed to, it must be obeyed. The reaction to fire performances must be known by test reports and certifications of the products. And the architects and engineers must have a basic understanding, at least, of the materials to select the correct materials and to install the correct materials. So everyone, every technical person should learn about and apply the regulation responsibilities. Or we will face, of course, fires, mortal losses, casualties in fires, and most probably legal responsibilities, court cases, and a heavy conscious responsibility as well. So to be in peace of mind against the fire disaster, we should increase our knowledge and know about application of the fire codes inside our country. Thank you very much.